Okay, section 14.2, we're going to talk about the properties of limits. The properties of limits are going to help us find definite answers to the strong evidence that we produced in section 14.1, where we use the calculator to evaluate limits. The first thing we're going to do is we're going to find the limit of a constant function and the identity function. We're going to use properties of limits. We're going to find the limit of polynomial functions and rational functions, and we're going to use the limit theorem. So first of all, let's talk about the limit of a constant. And here you have a constant function. You notice that you have a constant function because it's a horizontal line. So to make this a little easier to understand, let's say this is the line y equals 5, or f of x equals 5. It is a function because it passes the vertical line test. Now, if we're finding the limit as x approaches some number c of that function, it's always going to be 5. So because it's always closing, if you're closing in here and at this value, then your y value is always at 5. So let's look at a couple of examples. If you've got the limit as x approaches 1 of f of x, then that's just going to be 5. And if we have the limit of f of x as x is approaching, let's say, 2, then we still get 5, and so on. And, if you were to change this to 0, this is still going to be 5. If you were to change it to negative 100, it's still going to be 5. So that's how the limit of a constant works. It's always going to be, you're always going to say it's equal to whatever that constant value is. All right, now we have the limit of the identity function. Now let's be reminded of what the identity function is. It's the function f of x is equal to x, or the line y equals x, and we have a graph of line y equals x here. And this says that the limit of the identity function and as x approaches c is just equal to c, and that's because if you plug in c some value 5, if x is equal to 5, then y is equal to 5, and so on. So let's look at a couple of examples on this one. The limit of a constant function, which is f of x, or just x, so you could write it like that, or you could write this either way, as x approaches 1 is just going to be 1. And then we could also say that the limit as x approaches negative 2 is equal to negative 2. And we could continue this. The limit as x approaches negative 100 is negative 100. All right, and so there we have the limit of identity function. And then that takes us over to the properties. Now these properties, they sort of look a little more complicated than what they are. And this is in your textbook too. But a couple of things that you just need to know in dealing with these here. So the first one is that if you have the sum of the two, f and g, then that can be rewritten as this. The limit of f of x plus the limit of g of x, which is just the limit of f of x would be L, the limit of g of x would be M. So let's just review a couple of things really quick, and then those are sort of pretty easy to understand. First of all, let's just come up with a couple of functions. Let's say f of x is 4 and g of x is x. Then if we have f, then that's just f of x plus g of x. And the same thing if you're subtracting, so we just end up with x plus 4. Okay, and that's going to help us evaluate these limits here. Let's look at multiplication. It's going to work. Division is going to work the same way. If we have this, then that's just 4 times x. And if I have f over g, x, then f4 over x. And if I have the square root of f of x, then that's just going to be, in this case, the square root of 4, which would end up being a constant term. Okay, so that's a review of operations with the functions. And so now that we know the properties of these, and we're just going to put that to work here with this. So previously what we've done is just looked at a graph and come up with a t-table to help us evaluate these limits. But now we're going to take that a step further, and we are looking for the limit of f of x as x approaches -2, and f of x being this time the x squared plus 3x minus 6. So given those properties of limits, then I can rewrite, okay, so this is what I'm looking for. And I'm just going to write f of x too, so it can be a little shorter. And actually, no, let's go back and write out the whole thing so you can understand where I'm going with this. X squared. All right, so once I have that, then you notice that I've got x squared plus 3x minus 6. I can rewrite those as, suppose, you know, the x squared is your g of x, your 3x is going to be your h of x, and your -6 is your s of x. Then I can rewrite this as it's equal to the limit as x approaches. Okay, so I have that. Now, what you want to try to do is think about what we've talked about so far. We've talked about limits of the identity function and limit of constants. And if we can break it down into just identities and constants, the identity function and constant function, then we can go ahead and evaluate. So right now we've got x squared, so that's just x times x. And using that property, we can change that to x times okay, so this guy here turned into these two. And now we're going to deal with our 3x, so I'm going to say plus and then we've got times. Okay, and then plus. Okay, now at this point you notice that everything we're dealing with, the x, the 3, the x, and the -6, they're all either a constant or the identity function. And so now that we have that, using the properties that we talked about, the limit of the identity function is just going to give me -2 times, and then again -2 plus, and here we're always going to get 3 times, and then we have the identity function again, so we get -2, and then we have the constant function, so we're going to say plus -6, and then we go through, evaluate this, and we come up with -8. Okay, so the limit of f of x as x approaches -2 is going to be -8, and that would be the algebraic way, using the properties that we would do it without using the graph. You could go and look at the graph of this and make sure you do agree. So now that's quite a long process, so we're going to learn sort of a shortcut here with polynomial functions, the limits of polynomial functions. If f of x is a polynomial and c is any real number, then the limit of f of x as x approaches c is just going to be f of c. And this is sort of what we've talked about, is that oftentimes the limit is just going to be if you evaluate f, the function f, at the point c. And when it's a polynomial function, that's always the case. So we probably need a little bit of a review about what a polynomial function is. A polynomial function is going to be an algebraic expression or function with an algebraic expression that has exponents that are non-negative integers. So all right, so non-negative integers also, you know, implies that you have no exponents in the, no variables no variables in the denominator. Okay, and so now that we know that, let's move on and talk about the rational function. So rational function is very similar. It's just that when you're also going, when you're finding the limit of a rational expression f of x as x approaches c, you're also going to find f of c, as long as c is defined at that point. So we'll have to talk about something else in the event that c is not defined at that point. So a function, a rational function, is just going to be a function whose rule is the quotient of two polynomials. So if you have two polynomial functions and one divided by the other, so for example, that could be x squared plus 2 over x minus 1. So you have the quotient of two polynomial functions. This would be an example. Now, this would not apply to the case where c is equal to 1 because it would not be defined at that point. And then we talk about the limit theorem. Now the limit theorem is going to help us deal with that case that we talked about over here where it's not defined where c is equal to 1. So the limit theorem says that if f and g are functions that have limits as x approaches c, and f of x is equal to g of x for all x not equal to c, then basically the behavior of f of x and g of x up to that point c are the same. So the limit of f of x as x approaches c is going to be the same as the limit of g of x as x approaches c. So meaning that if you simplify it, you can just use this. So for example, what this is saying is, let's say I have a function s of x, and it's equal to x plus 1 over x plus 2. Times x plus 2 over x plus 2. Well, you know that this function is undefined where x is equal to negative 2. These could cancel out and giving us basically a linear. So the behavior of f of x is going to be the same as just the line x plus 1, except for at x equals negative 2. And so in using this, here, let's say I defined let's call this h of x. Let's say I said h of x is x plus 1. Then what this means is that when I wanted to find the limit of s of x as x was approaching negative 2, it's undefined there. So if I simplify it, I notice that the behavior up to that point is the same as the behavior of h of x. So all I really have to do is find the limit of h of x, which is x plus 1, which is just a polynomial function, of negative 2. So in this case, you would just plug in the negative 2. So it's saying that those two are equivalent. So we will be using the limit theorem quite a bit. All right, now we have a couple of examples. All right, so you've got f of x here, and f of x, you notice, is a rational function. The numerator will not factor here, but the denominator can factor as x minus 2, x plus 1. Okay, so you notice you have a couple points at which it's undefined. Right now we're looking for the limit of f of x as x approaches negative 4. So we don't have an issue. So we have a rational function. We want to know what's happening as the limit as x is approaching negative 4. This means that I can just go back and use the rule on the limits of rational functions. I don't have to get into the limit theorem in this case. So all I need to do here is just plug in that value and find out what f of negative 4 is. So if I find f of negative 4, I'm going to get negative 4 cubed. Okay, I get this. Okay, and we simplify to negative 28 over 18, which is going to simplify to negative 14 over 9. Okay, so since f of negative 4 is equal to negative 14 over 9, then I can come up here and say that this limit is, okay, and this is an example of one of these that's much easier to, well, the only way to find the exact value is using the algebra, not using your calculator. If you use your calculator, you're going to see you're going to have a hard time figuring out to what decimal place you're going to round, or actually figuring out that you have negative 14/9 is the limit that we're looking for. Okay. Here's the next example. Again, we have a rational function because you've got one polynomial divided by another polynomial, or the quotient of two polynomials. This time we're looking for the limit of f of x as x approaches negative 2. You notice in this case that for f of x, x equals negative 2 is not in its domain. So if it's not in its domain, then we need to figure out what to do. So we're going to use a limit theorem. We know that f of x can be factored, the numerator can be factored as x minus 4 is x plus 2. And you've got x plus 2 here, which means that f of x is going to have the same behavior as g of x, which would be equal to x minus 4, except at for all values except for where x is equal to negative 2. So the behavior between g of x and f of x are going to be exactly the same except for where x is equal to negative 2. So that's because this is not in the domain of f of x. So what that means is that since they have the exact same behavior, then the limit of f of x as x approaches negative 2 is going to be the same as the limit of g of x as x approaches negative 2. Now you notice that g of x is a polynomial function, so all we have to do is say plug in negative 2 for the x in that value. So we have negative 2 minus 4, and that's going to give me negative 6. Okay, so the limit of f of x as x approaches negative 2 is going to be negative 6, and that's using the limit theorem that we were able to come to that conclusion. And that's all I have for section 14.2. In the next section, we'll talk about two-sided limits.